Good morning, everyone.
Good morning.
How are you?
I'm good. How are you?
Doing good, thank you. So today's is a review session for the exam two, and I hope you do great in exam two as you did in exam one. And today I will go over the chapters what will be covered in the exam, chapter four, chapter five, chapter six. And the format for the exam will be similar to the exam one, and you need a calculator. Simple calculator is fine. And the exam will be like a short answer calculation, but I will not ask you to do anything by R during the exam. Okay, if you have any question, let me know about the exam. I will come to the class early, something like 10 or 15 minutes, just in case if you would like to start the exam early. Okay, any questions? Any questions? Okay, so let me go over the three chapters. And if you have any question at any time, please unmute yourself and ask the question at any time. Okay? Let me set up my computer. Okay, do you see the whiteboard? You see the
Yes.
whiteboard? Thank you. So the exam will cover chapter 4 up to chapter 6. So 4, 5, 6. For each, in these chapters, we covered many designs. We covered the complete randomized block design, lattice square design, and so on. So for each design, you need to be familiar with the requirements for each design. You need to be familiar with the assumptions or ANOVA. And the three assumptions are always independent, constant variance, normality. But the requirements for each design is different from design to design, but the assumptions of ANOVA or the assumption of the model are the same: independent, constant variance, normality. So you need to test these three every time for each design. But in the exam, I will not ask you to test this one using R, but maybe I will give you output and ask you about this output, if the assumptions are satisfied or not. And also you need to familiar with the statistical model for each design. You need to be familiar with the interpretation of the R output. So I give you some R output and you should be able to interpret or understand these numbers. Whatever the R output is a plot or some numerical summary or some numerical analysis. And you need to be familiar with the layout of each design. You need to be familiar with the differences between designs. And if I give you some scenario, you should be able to know this design is what, this scenario is, which design should be used. Okay, so let me start by chapter 4. Chapter 4 is about, in chapter 4, we have only one treatment factor, but sometimes we have one blocking factor, maybe two treatment factor, three treatment factors, and so on. So the first design we covered in chapter 4 is is complete randomized block design. The first design we covered is complete randomized block design. In complete randomized block design, we have only one treatment factor, has A levels, and we have one blocking factor, has B levels. It is not necessary to be the same. And the requirements of this design, is there is no interaction between the blocking factor and the treatment factor. Requirement, no interaction between blocking factor and treatment factor. But the assumptions are the same. Assumption independent constant variance normality, those assumptions for the ANOVA test. But the requirements for this design, we shouldn't have interaction between the blocking factor and the treatment factor, unless the block is big enough to test each treatment more than one time. So the layout of this design. In this design, in complete randomized block design, we assume that each block is big enough to test all the treatments. If you test all the treatments, each treatment only one time, the interaction between the blocking factor and the treatment factor should be exist. But if you are able to test each treatment more than one time within each block, you can test the interaction. You can include the interaction in the ANOVA table. You can include the interaction in the statistical model and so on. But let's assume that we do not have much resources and we are able to test all the treatments within each block. Each treatment tested only one time. Let's assume we have T1, T2, T3, T4. So the first one maybe is used to test T1 first, and then T3, and then T2, and then T4. The second block is used to test T1, T2, T4, T3. The last block, this one number 1, number 2, up to block number B. They're big enough to test all the treatments, and assume you have 4 treatments. So what is the statistical model? The statistical model in this case is Yij equal mu plus tau I plus beta j plus epsilon ij. I is 1, 2, up to how many treatments we have? A. J is 1, 2, up to how many blocks we have? B. So this is a statistical model. If you have replication, you add K, like Yij K. But within each block, we have each treatment tested only one time. So we have no replication within each block. And you should be familiar with the ANOVA table. and you interpret the ANOVA table, use the ANOVA table to test the treatment factor is significant or not, the blocking factor is significant or not. But we shouldn't include the interaction in the ANOVA table because we assume there is no interaction. And the assumptions for ANOVA table again are independent, constant variance, normality. We tested these ones many times. So this is the first design we covered in chapter 4. Guys, if you have any question at any time, please let me know. At any time, stop me at any time. The second treatment, the second design we covered is Latin square design. In Latin square design, we have one treatment factor each it has P levels, and we have two blocking factors, each has B level. So we have three factors, two blocking factors and one treatment factor, each has B level. And the statistical model in this case, Yi, J, K. I for the first treatment factor, J for the first blocking factor, K for the second blocking factor, equal mu plus alpha I plus tau J plus beta K. So we have three effects for the three factors, alpha, tau, beta. Alpha for the first blocking factor, tau for the treatment factor, beta for the second blocking factor, plus epsilon I, J, K. And there is no replication, so there is no L. I equal 1, 2 up to number of levels B. J is 1, 2 up to number of levels B. K is 1, 2 up to number of levels B. Because each factor has the same number of levels B. And the requirements are, there is no interaction between any two factors. There is no interaction between any two factors. We have three factors, one treatment factor and two blocking factors. There is no interaction between any two of them. And each factor has the same number of levels, which is B. All factors have the same number of levels. If one of them has a different number of levels, so this design doesn't work. You shouldn't use this design. You should use something else. So for example, to give me the layout for some example, layout, let's assume P equals 3. So each factor has 3 levels. So how do I write down the layout? We assume the rows are the blocks of the first blocking factor, and we have 3 levels. And the columns are the blocks of the second blocking factor. And the treatments, let's assume T1, T2, T3, or ABC, or any notation. We worked with ABC. So how do I assign the treatments within each block and within each row, within each column and within which row, such that each treatment will be tested only one time within each row and only one time within each column? So there are many ways. This is one of them. A, B, C, B, C, C, A, B, and this one should be A. This is one of the assignments. So for the first block of the first treatment factor, first block of the second blocking factor, assign A and then measure the response. To the last one, so how many values I will have? I will have 9 values in this case. So this is the layout when we have 3 factors, 2 are blocking factors and 1 is treatment factor, and each have 3 levels. And again, you should be familiar with ANOVA. In the ANOVA, we will have 3 p-values. One for the first treatment factor, and the second one for the first blocking factor, and the third p-value for the second blocking factor. And there is no interaction in the ANOVA table. And you should be familiar with the assumptions again. The assumptions are independent, constant variance, normality. So this is the second design we covered in chapter 4. If you have any question, please let me know. The third design we covered in chapter 4 is Greco-Latin square design. In Greco-Latin square design, we have 1 treatment factor again. And we have 3 blocking factors. 3 confounding variables we control their effects. And the requirements are what? The requirements are no interaction between any 2 factors. No interaction between any 2 factors. We have 4 factors. No interaction between any 2 factors. And all the factors have the same number of levels. All factors have the same number of levels, which is P. So the statistical model can be written as YIJKL. I for the first treatment, the blocking factor, J for the treatment factor, K for the second blocking factor, L for the third blocking factor. You can use any notations like mu plus theta I plus tau J plus gamma K plus XIL plus the error epsilon IJKL. And I is 1 to up to P, J is 1 to up to P, K is 1 to up to P, L is 1 to up to P. Have the same number of levels. If one of them doesn't have the same number of levels, you shouldn't use Greco-Latin square design. You should use some other design. So one of the examples, if P equal 3, if P equals 3, the layout, again we will use the rows are the blocks for the first blocking factor, and columns are the blocks of the second blocking factor. What about the third blocking factor? You need to give some notation like alpha, beta, gamma. So assuming the first blocking factor has 3 levels, the second blocking factor has 3 levels, and the third blocking factor has 3 levels, let's call them alpha, beta, gamma, or any notations. So how do I randomly assign for each combination of the 3 blocking factors? You assign a treatment. So for example, the first blocking factor, the first block of the first blocking factor, the first block of the second blocking factor, and the first block of the third blocking factor, assign a treatment A and then measure the response. You need to assign these ones such that each treatment should appear only 1 time within each row and only 1 time within each column. And each combination of the third blocking factor and the treatment factor appear only 1 time. So in this case, I see A alpha. I shouldn't see any A alpha again, and so on. So if you do by hand, it's not easy. So you ask R to give me this randomization. So in this case, this one should be B beta, C, gamma. This one should be C, beta, A, or A, gamma, and then P, alpha, and then B, gamma, and then C, alpha, and then A, beta. This is the layout for the Greco-Latin square design when we have 3 levels for each treatment factor and blocking factor. And also you should be familiar with the ANOVA. ANOVA will have how many p-values? We will have 4 p-values. 1 for the treatment factor and 3 for the blocking factors. There is no p-values for the interaction because we assume there is no interaction. And we should be familiar with the assumptions also. Assumptions again are independent, constant variance, normality. They are the same all the time. This is the third design we covered in chapter 4. The last one we covered in chapter 4 is balanced incomplete block design. Balanced incomplete block design. In this design, we have 1 treatment factor and 1 blocking factor. So it should be balanced incomplete. It should be complete randomized block design. But the problem here is each block is not big enough to test all the treatments like complete randomized block design. Each block is smaller than the number of units in each block is smaller than the number of treatments. So this is why we use incomplete block design, but we make it balanced incomplete block design because the balanced incomplete block design is better than incomplete block design. So in this case, the block is not enough to test all the treatments. The requirements of this design to have a balanced incomplete block design the first one is the blocks have the same number of the same size. Blocks have the same size. The second requirement is each treatment repeated or tested the same number of times. Each treatment tested the same number of times. The third requirement is each pair of treatments appear together the same number of times. So let's have an example. If I have 4 treatments, let's call them T1, T2, T3, T4, or 4 treatments A, B, C, D, any notation, like let's use A, B, C, D, or T1, T2, T3, T4, any notation. So, and assume each block is big enough to test only 3. Test only 3. Let's assume we have 4. So the first block is used to test treatment A, treatment B, treatment C. Second one is treatment A, treatment B, treatment D. Third one is treatment A, treatment C, treatment D. Last one is treatment B, C, D. Let's see this one is balanced incomplete block design or not. Each block has the same number of size. The first one is 3, second one is 3, third one is 3, fourth one is 3. Each treatment tested the same number of times. A tested 1, 2, 3. B tested 1, 2, 3. C tested 1, 2, 3. 4 tested 1, 2, 3. The last requirement, each pair of treatments appear together the same number of times. And when I look at the first block, I see AB appear one time. In the second one, AB one time. So far, AB appear together two times. I do not see AB in the third one. I do not see AB in the fourth one. So far, AB repeated two times. So any other pair of treatments should appear the same number of times. So let's see AC. AC appear together two times. AD two times. BC two times. CD two times. So this one is balanced incomplete block design. So this is the layout when we have 4 treatment factors and 4 blocks. And the block is not big enough to test all the treatments. And you should be familiar with the ANOVA table. In the ANOVA, I will have only 2 p-values, one for the treatment factor and one for the blocking factor. And you should be familiar with the assumptions of ANOVA again. The assumptions are independent, constant variance, normality. So what is the statistical model? The statistical model is Yij equal mu plus tau I plus beta j plus epsilon ij. So this is the complete randomized block design, a statistical model. The difference is I is 1 to up to A, but J is not 1 to up to B. It is 1 to up to Ni. Ni. Or so how many times each block has number of units. So this is the balanced incomplete block design. This is the last design we covered in chapter 4. Any question about chapter 4? Okay, let's go to chapter 5. Chapter 5 is factorial design. Because so far up to chapter 4, we work all the time with one treatment factor, but now we need to increase the number of factors. So the number of factors may be two treatment factors, or 3, or 4, or 5, or 6, or 7, or 8, any number of treatment factors. We covered 2 factors, but this one can be extended to any number of treatment factors. But in chapter 4, we didn't include any blocking factor. We cover the idea of if we have many treatment factors. So if you have only 2 treatment factors, and as an example, 2 treatment factors, let's say A and B. There's two treatment factors. The first one has A level, second one has B levels, or any notation. The statistical model in this case, if we have 2 treatment factors, Yij equal mu plus tau I plus beta j plus the interaction tau beta ij. Why you are able to test the interaction? Because in this case we have replication, so y will be Yij k. Each treatment will be tested more than one time. So plus epsilon ij k. So I equal the number of levels of the first treatment factor, 1, 2, up to A. J is 1, 2, up to how many levels? Second treatment factor, let's say B. K is 1, 2, up to how many times each treatment tested? Let's say N. This is statistical model. In the ANOVA table, you will have how many p-values? You will have one p-value for the first treatment factor, one for the second treatment factor, one for the interaction. So in this case, this is our first time to include the interaction in the ANOVA table, and we will be able to test the interaction. So this is why you will have three null and alternative hypotheses. The first one, null and alternative for the first treatment factor. The second one, H0, H1, will be for the second treatment factor. H0, H1 for the interaction between the two treatment factors. The first one can be written as mu1 equal mu2 up to mu versus at least one is different. Second one will be mu1 equal mu2 up to mu b versus at least one is different. The third one, you can write it down as no interaction, there is interaction. Or you can write it down as tau beta I j equals 0 for all I and j. This one, at least one is not 0. Or this one can be written as, there are many ways to write down H0 and H1. No interaction. This one can be written as there is interaction. Also can be written as mu11 equal mu12 equal mu up to equal mu AB. So there are many ways to write down H0 and H1. So you will have one p-value for the first treatment factor, another p-value for the second treatment factor, one more value for the third blocking factors. And so which p-value I should look at? Look at this one. The p-value for the interaction. This is the first one you should look at. Because if this p-value is big, it means the two treatment factors are independent. So you can test each one separately from the other. If this value is big, it means you fail to reject H0. It means there is no interaction. But if this p-value is small, it means A and B interact. So it means when you test A, it should be at some level of B. When you test the second treatment factor, it should be at some level of the first blocking factor, the first treatment factor. So again, if this is the first p-value you should look at, the p-value of the interaction. If this p-value is greater than the significance level, you fail to reject H0, it means there is no interaction. It means A, the first treatment factor and the second treatment factor are independent. So independent means you can test each one separately. You can look at this p-value to test the first treatment factor. You can look at this one to test the second blocking factor, second treatment factor. But if this one is smaller than the significance level, it means the interaction is significant. So when you test this one, it should be at some level of this one. When you test this one, it should be at some level of this one. When you do multiple comparison for this one, it should be at some level of this one. When you do multiple comparison for this one, it should be at some level of this one. If they interact. How do I know they are interact or not? You can look at the interaction plot. But it's better to look at the p-value more than the interaction. But you can explore the interaction using the interaction plot. So, and keep in your mind, again, when you do multiple comparisons, for one treatment factor, it should be at some level of the second treatment factor if the interaction is significant. But if the interaction is not significant, you can do multiple comparison for the first one. In general, you can do multiple comparison for the second one. In general, you don't look at the other one. So what about the layout? There are many ways to write down the layout. If we have two treatment factors, so you can write the levels for the first treatment factor like 1, 2, up to A, because we assume the first one has A levels, second one has B levels. So within each level of the first treatment factor, you have the levels of the second treatment factor, and so on, like this way. This is one way to write down the layout, but there are many other ways. So this is chapter 5. This one can be generalized to any number of treatment factors. Any question about chapter 5? Okay, chapter 6. Why we have chapter 6? Because in chapter 5 there is a problem. What is the problem in chapter 5? In chapter 5, we have many treatment factors. Maybe the first one has 3 levels, second one has 4 levels, the third one has 5 levels. So number of treatments will be 3 times 4 times 5, which is 12 times 5 is 60. And if you need to have replication, you should test each treatment at least 2 times. So the number of required experimental units is at least 2 times 60 is 120. So sometimes 120 experimental units are not available. You do not have this much resources. So you need 120, at least 120 experimental units to see these 3 treatment factors are significant or not. So this is too much sometimes, like no way to work with 120 horses, for example, or 120 patients, they have some rare disease. So this is why we decide in chapter 6 to work with only two levels for each treatment factor. So we change this one to be 2, 2, 2. In this case, number of treatments will be 2 times 2 times 2 is only 8. And the number of required experimental units, if you have only 2 replicates, it will be 2 times 8, 16. So see, you saved how much resources from 120 to 16 by working with only 2 levels for each treatment factor, better than working with many levels. So chapter 5 is similar to chapter 6, but the difference is what? We work with only 2 levels. So we call it 2 to the power k factorial design. 2 to the power k factorial design means we have k treatment factors, each has only 2 levels. So each treatment factor has only 2 levels. So assume that, for example, let's assume we have only 2 treatment factors. Example, 2 to the power 2 factorial design. If you have only 2 factors, each has 2 levels, but it can be extended to any number of treatment factors. In this case, the statistical model will be Yij k, because we have replication. In this chapter, we cover 2 cases, with replication, without replication. So if you have k, it means you have replication. If Yij only, there is no replication. So Yijk equal mu plus tau r plus beta j plus tau beta ij plus epsilon ijk. This is the same statistical model in chapter 5, but the difference is I is 1, 2, j is 1, 2, k is 1, 2. Okay. K is 1, 2 up to any number like little n, because number of replicates is not required to be 2, can be any number. But the number of levels of each treatment factor, only 2 levels. And let me give you the idea of pluses and minuses. Because in this case, we have 2 treatment factors, let's say A and B. And this one has 2 levels, this one has 2 levels. So these 2 levels can be written as high, low, or plus, minus, plus, minus. So in this case, we can write the table as that we use to calculate the main effect and an action effect. A column for A, column for B, and then replicates. If you have only one number, there is no replication. You have many numbers, it means each treatment tested more than one time. What are these treatments? The treatments are the combinations, like A is low, B is low. This is a treatment, we call it 1. A is high, B is low. This is treatment A. Maybe A is low, B is high. So this one is treatment B. Maybe A is high, B is high. This is treatment AB. We call them these are, or you can call them T1, T2, T3, T4, but we use this notation. And you have replication. If you have only one value for each treatment, so no replication. This is a problem. We will talk about this one in a few minutes. But if you can test each treatment more than one time, so you have many values for each treatment. You tested each treatment more than one time, it means you have replication. So how do I estimate the main effect and reaction effect? Because you need to be familiar with how do I calculate the main effect and interaction effect. It's very simple. The average of pluses minus the average of minuses. So if I would like to calculate the main effect of A has 2 minuses and 2 pluses. So for the pluses, I can calculate the average by calculating the average of these 6 values. So you sum these 6 values, divide by 6. It gives me the main, they give me the average under pluses. And I have 2 minuses. So the average of these 6 values give me the average under minus. And the difference between the average under plus and minus the average under minus give me the main effect of A. You can do the same thing with B. And if you'd like to estimate the interaction AB, you need to have a column AB. So you need to multiply A times B. Minus times minus gave me plus. Plus times the minus gave me minus. Minus times the plus gave me minus. Plus times the plus gave me plus. So again, I will have 2 pluses, 2 minuses. If I would like to calculate the interaction effect AB, I calculate the average of plus minus the average of minus. For V, I have 2 pluses. So the average of these 6 values minus the average of these 6 values gave me the interaction effect AB. This is how I estimate the interaction effect and the main effect for the 2 to the power k factorial design. And this case is the replicated design. In this case, we have replication. This is with replication. With replication is this similar to chapter 5. The only difference is I have only 2 levels for each treatment factor. And the estimation of the main effect and reaction effect is very simple. And also ANOVA table. In the ANOVA table, I can test the main effect of A, main effect of B, interaction between A and B. I can include all the effect in the ANOVA table. Why? Because I have replication. Having replication means you have enough degree freedom to estimate all the main effect and interaction effect and the experimental error sigma square and test all of them because you have plenty of degree freedom. And be familiar with the assumptions, the 3 assumptions again. But if you have no replication, in this case, there is a problem. The problem is what? You will be able to estimate the main effect and reaction effect, but you will not be able to go to the ANOVA table and test all of them simultaneously. Why? Because the degree freedom you have is enough to estimate all of them, but is not enough to test all of them. Why is not enough to test all of them? Because to test all of them at the same time, you need to have the estimation of sigma square. And you spend all the degree freedom you have to estimate the main effect and reaction effect, and there is no degree freedom left to estimate sigma square. So what is the solution of this problem? The solution is, after you estimate all the main effect and reaction effect, you need to remove at least one of them. So you get the degree freedom of the one you removed and estimate sigma square. But maybe you remove many of them. But when you remove, you should remove something that is expected to be not significant. So how do I remove some of the main effect or the interaction effect? There are many ways covered. So in this case, you have A, you have B, you have AB, you have only one replicate. Like a number, a number, a number, a number. Minus, minus, plus, minus, minus, plus, plus, plus. And this one is plus, this one is minus, this one is minus, this one is plus. This case, I have only one replicate. Can I estimate the main effect of A, main effect of B, an interaction between A and B? You can do it. The problem is not estimation. The problem is testing. So you will be able to estimate A, estimate B, estimate AB, but you cannot go to the ANOVA table and test these effects, because in the ANOVA table, I need also to estimate sigma square, and there is no degree freedom left to estimate sigma square. So what should I do? You can use one of these methods. The normal probability plot, or half normal probability plot, or Pareto plot, or reference plot. These are different methods. Sometimes, most of the times, they recommend the same thing, but sometimes different ones. In the normal probability plot, in the normal probability plot, we compare the effects values to the normal data. If these normal data with mean 0, so if these the values are very close to 0, will be very close to the straight line, like this one, this one, this one, this one. If there is something far away from the straight line, it is considered not close to 0. So you need to include this one. If you have one more, this one. So you include only the ones are far away from the straight line. The normal probability, the half normal probability plot is the same normal probability plot, but we multiply the negative ones. If this one is negative, so you multiply by -1, you get positive. So you will find all the big ones. Maybe you have a small one like this far away. So all of them on one side. Like this one, this one, this one. And the other ones will be close to the straight line, should be removed from the ANOVA table and save this degree freedom. So you can count how many degree freedom you save is the number of effects very close to the straight line. Or you can use Pareto plot. Pareto plot order the effects based on the value. And you should include anything higher than the margin of error. But if you see all of them are higher than the margin of error and you need to remove at least one, you can use the simultaneous margin of error. And one more method is the reference plot that give you a graph of the half standard normal distribution. The mean is 0, and you exclude the ones are close to 0, and you include the ones far away from 0. So using these methods, I can remove at least one of the effects, so I can get at least 1 degree freedom will be used to estimate sigma square. So I can go to the ANOVA table and include only the ones selected to be included in the ANOVA table and be tested. And you remove all the ones that recommended to be removed. But this one is this 2 to the power k factorial design with no replication is very nice in terms of saving resources. But the problem is outliers. You should be very careful when you measure the response, because if this one is outlier, so it means when you measure the response, you didn't measure the response accurately, and this one is wrong, everything will be wrong. So you should be very careful when you work with 2 to the power k factorial design with no replication. But with replication is fine, because having replication make your life easy. But it means you have much resources. But in many cases, we do not have much resources. So we have to work with something doesn't need much resources. This is chapter 6. Those are the 3 chapters will be covered in the exam. Do you have any questions? As I said, I will come to the class early as much as I can, so you can start the exam early if you need. time. Because some students they feel good when you feel like I have much time. So I will come to the class early so you can start the exam early. Any question?
Will you please go over how to do the or how to calculate the main and interaction effects again from the plus and minuses table?
Okay. If you have these values like 3, 2, 7, 8, I would like to estimate the main effect of A, main effect of B, interaction between A and B. If you'd like to estimate the main effect of A, you have 2 minuses and you have 2 pluses. So the average of plus, this one is plus and this one is plus. So it will be 2 plus 8 divided by how many values? It's 2 values. Minus, these ones are minuses. So 3 and 7. 3 plus 7 divided by 2. This one is the main effect of A. You do the same thing for B. What about interaction AB? This one also has 2 pluses and 2 minuses. This one is plus, this one is plus. So it will be 3 plus 8 divided by 2 minus these two are minuses. So 2 and 7. 2 plus 7 divided by 2. This one is the interaction AB. So in this case, you have only 2 treatment factors, A and B. Maybe you have A, B, C. So the combination, so A column will have 4 pluses and 4 minuses. B have 4 pluses and 4 minuses. B have 4 pluses and minuses. The main idea is, how do I calculate the main effect? The average under plus minus the average under minus. Does it answer the question?
Yes, thank you.
If you have more values, like if you have replication, like this case, you have more values, 1, 2, 3. So when you calculate the main effect of A, it will be the sum of these values plus the sum of these values. So this one plus 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 this one. So you divide by 6. Minus this one plus 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 this one, divide by 6. It gives me the main effect of A. Got it? Any other questions?
How to calculate the treatment mean?
Excuse me?
How do I calculate the mean treatment mean? There is a question in
How do you calculate different means?
treatment mean. Mean of treatment.
Mean of treatments?
Yeah.
The mean of treatments is the one is covered in chapter 3.
There was a question in homework 6 to calculate like
This one. If I asked you to calculate the treatment means, this one was in chapter 3. So
Okay.
in the coming chapters, I will not ask you, but you can do by hand. It's very simple. How do I do it? Okay, let me show you how to do it. Because in this case, how many treatments you have? You have 4. Minus minus is a treatment. Plus minus is a treatment. Minus plus is a treatment. Plus plus is a treatment. So how do I calculate estimate these treatments? So the average of these ones minus mu give me the treatment of okay, let me explain in more detail. This one is called mu ij. This one is called mu ij. So if you calculated the average for this one, this is the first treatment. If you calculate the average of this one, it will be the estimation of this one. So mu ij है. So the sum of the 3 values divided by 3 give me mu ij. And mu ij is the estimation of mu plus tau I plus beta j plus the tau beta ij. In this case, if I asked you estimate the tau I only, one would be a little complicated. So this is why you ask R to give it to you. So in the chapter, I don't remember chapter 3 or 4, what I asked you, we practice on R to ask R to give me the estimation of tau I, beta j, tau beta ij by R, but it's not by hand. By hand is not easy. But in chapter 3, it was easy to show you how to estimate tau I, tau 1, tau 2, tau 3, and so on. So I will not ask you to estimate the treatment effects in these chapters, because I'm
Thank
not
you.
going to ask you to do anything by R
Okay.
during the
Thank
exam.
you.
Okay. Any other
Um,
questions? Yeah, sure.
yeah, I got one. When we do the Levene test to check the ANOVA assumptions, for example, for 2K factorial design, I did a Levene test with like for the homework with like different factors as like the main factor and got the same. It was both equal variance, like it had the same end result, but got different p-values. So I was wondering, do we have to run it several times or just once?
Can you, because I think you can send me the code you have, and I will see which one is correct. But
Okay.
some people do Levene test if you have three treatment factors like A, B, C. Some
Yeah.
people do the Levene test for A, Levene test for B, Levene test for C.
Yeah.
And also Levene test for AB, Levene test for AC, Levene test for BC, Levene test for ABC. But some people do the Levene test for only this one because the combination is the treatments. So when you run LM and then give a response and then tell give me the higher order of reaction A times B times C. So they test the Levene test for the combinations because the combination are treatments. But some people do the Levene test for this one, this one, this one, this one, this one, this one.
But doing this for this one would be enough total.
Yeah, this is
Oh,
enough.
okay, that's great.
Okay.
The second one is the matrices with plus and minus. Do we have to have them in the formula sheet or would they be there if we need them?
It's very simple, but if you'd like to have an example for this one, is fine. Example like this one, if you would like to have the pluses and minuses of this one, is fine. So, and then in your mind, you can extend this one to any number of treatment factors.
Yeah, I didn't mean an example. I just meant like the actual matrix.
Yeah, because there are many actual matrix, like it depends on how many treatments you have.
Yeah,
Because if you can write one of them, it's fine, but actually the idea is very simple. Like you have a column for A, column for B, and then the multiplication and these kind of things. But if
yeah,
you'd
but
like to
like
have one like this one, it's fine.
okay, so it would be provided if we are like supposed to use the interaction effect for
Yeah,
2
yeah,
to the
that's
power of
correct.
4, it would be there. Okay.
And if there is nothing, if I asked you to get the interaction between A, B, C,
Yeah, okay,
but I
that's
gave you the column for A, column for B, column for C, you multiply these three columns.
yeah. Okay.
Okay. Any other questions?
Can you bring formula sheet?
Can I provide a formula sheet?
No, I mean, last time we brought our own.
Yeah, you can have a formula sheet.
Yeah.
I think did I mention? I think I mentioned this one in the guidelines, or I didn't mention. Because you can have a formula sheet as an exam one. I will double check if I
Yeah.
didn't mention that you can have a formula sheet or not. Yeah, because you need to have a formula sheet.
Yeah. Thank you.
Thank you. Any other questions?
How do we read the like ANOVA assumption test on R, like the Shapiro tests? Are those the ones where like a high p-value is good?
You mean how do I test the assumptions? If the
Yes.
p-value
Yeah.
is big, it means the assumption is satisfied. But some people use 5%, some people use 10%. Like if the p-value is greater than 10%, you assume the assumption is satisfied. But some other people use 5%, but most of the people use actually 10%. Like if the p-value is greater than 10%, the assumption is satisfied. If it is less than 10%, The assumption is not satisfied.
Okay,
Any
thank
other-
you.
You're welcome. Any other questions? Okay, have a great day, and I hope the exam will be easy and you do great in exam 2 as you did in exam 1. Thank you. Have a good
Thank you.
day. Thank you.